Welcome to lecture number 1, essentially, for the course material. We're going to cover today just an intro to what the Stern Gerlach experiment is, what it is, and essentially cover why classical mechanics and classical physics failed to explain it. So, a bit of history of the experiment. 1922, Otto Stern and Walter Gerlach devised this measurement essentially to test whether the angular momentum of silver atoms was quantized. And what they did is they had an oven that basically, and a collimator that sent out a beam of neutral silver atoms that went through a magnetic field gradient. So basically, they had a magnet like this, and established a field gradient in the z direction, we'll call it. Now, they didn't use permanent magnets like this. Their experiment actually had electromagnets, so they could turn on and off the field gradient. But basically, what they observed is when they shot this beam of silver atoms through this magnetic field gradient, it split the beam of silver atoms into two distinct paths. And they had a detector, essentially a screen, that was sensitive to when it was hit with these particles and would leave a little print on it. And what they saw was something like this. With the magnetic field gradient off, they just saw one solid sort of line beam resulting, hitting one spot on their detector. When they had the field gradient on, it actually opened up, and you saw sort of this splitting of that beam into two distinct bands. Little interesting story about this. Apparently, when they first performed their experiment, their silver beam was really weak. They hardly had any silver atoms going through in this thing. So the silver was should have been very, very faint when it hit the detector, and they should have had a much more difficult time seeing these bands. But apparently, Stern smoked very cheap cigars with a lot of sulfur in them. So when he was in the room performing this experiment, the sulfur from his breath would mix with the silver atoms and would form silver sulfide. And that had a much darker contrast on the screen, so you were able to see quite clearly what you see here, an actual image from their data showing the thing. But anyway, so that's what they saw. They saw you throw a beam through a magnetic field gradient, and what you got was a splitting of that beam into two distinct spots, two deflections, not a continuous broadening or anything like that. Right, so the question then becomes, well, how would we try to explain this, right? And let's just use physics we know from classical physics, stuff we've taken in previous courses. And the question becomes, well, how do neutral atoms interact with magnetic fields? And the answer is, well, let's say we have some atom that has some magnetic moment mu, and it's in some magnetic field described by some magnetic field vector B. We know that the potential energy of that moment in that magnetic field is just going to be mu dotted with the magnetic field vector B, right? And knowing that we now have this potential energy, we know that the force acting on a particle in a potential energy mu is given by the gradient of that potential energy. So if you're not familiar with this equation, you can think back to your classical 201 or whatever your intro physics was, and when we're looking at the potential energy on a simple harmonic oscillator, it is 1/2 kx squared. 1/2 kx squared, where we're plotting the potential energy as a function of position. And if we wanted to know the force at any point x, we can just take that force is equal to negative the derivative of that potential energy in one dimension. This derivative is essentially what this gradient means. And this would give us negative kx. So hopefully this is kind of an argument. If this equation here isn't as familiar to you, if you perhaps haven't taken 320 yet, or you don't recall from previous courses, the force is the gradient of the potential, negative the gradient of the potential energy. And a simple case we should all be familiar with it that we can sort of show as evidence of that is our simple harmonic oscillators that have our masses on a spring that have a potential energy of this. We can get Hooke's law, the force on a mass on a spring, just by taking the derivative of that. So if we do that in 3 dimensions, we end up with the force on this dipole is just going to be equal to negative the gradient. And if we write that out in full Cartesian coordinates, it's going to be partial x times our potential energy. And that's going to be the force in the x-hat direction. And we get the same sort of thing for the other 2 directions. Dot b, y-hat. And finally in the z direction, negative mu dot b. And that's in the z direction. Now, in the Stern Gerlach experiment, they essentially set it up so the gradient in the field was essentially entirely in the z direction. So this simplified to essentially, well, the negative signs would all cross out. This was just partial derivative in the z direction of mu dotted with b, these both being vector quantities, right? So the Stern Gerlach, if we analyze that experiment, what it ends up giving, we send those neutral atoms through that magnetic field gradient in the z direction, and we get a force in the z direction that is essentially, just because the magnetic moment of an atom is going to be constant, it's proportional to the field gradient in that z direction. So what does that mean, right? So if we've got a beam created in an oven, that means it's going to thermally randomize everything coming out of that oven. So if we've got a bunch of particles, each with their magnetic moment coming out, well, one might be aligned that way, but the next one would be aligned that way, then another one that way, and you just get this sort of random orientation of the magnetic moments. All of them are going to be sampled. So when these go through that magnetic field gradient, we have the beam coming this way. We've got some force in that z direction that's of a, it's proportional to the alignment of this and the gradient of that. It's going to push some up, some down, and it's going to be totally random in the way it does that. So what we would expect if we had our screen here, we would sort of expect some distribution, some broadening of that line, but continuous broadening. You just smudge it out in the z direction, because that force would be partially up and partially down. This is not what we saw. All right, in the Stern Gerlach experiment, what we saw was this sort of splitting of the beam into 2 distinct paths, one going up here, one going down here. So it seems that magnetic field gradient was constant for all the things coming up. There were only 2 possible angular or magnetic moments that these silver atoms could have, or at least 2 possible alignments of those magnetic moments in the z direction. So kind of a very weird result that classical mechanics, or a classical way of describing this, just failed to account for. So how can we sort of try and approach this? What is the magnetic moment of one of these atoms? Well, if we think of silver, it's got 47 electrons. Turns out if you go through the electronic configuration of it, it's only got 1 valence electron in the 5s orbital. That's the only one we're going to pay attention to right now. We've learned through atomic physics and all that. It's kind of putting the cart before the horse, because we learned a lot of this with quantum mechanics. But all those inner electrons in the valence, their angular momentum and their magnetic moments, we can think of as just canceling. So we have that 1 valence electron that's going to determine the magnetic moment of the atom. And if we think about that, what do we expect this to have? Well, if we have some nucleus of positive charge here, and if we view naively our electron as just orbiting that nucleus, just like a planet orbits the sun, sort of thing, and we approach that, well, this charge Q is going around that way. That looks like a current going in a loop, right? So we can think about that as a current equal to it's the amount of charge that crosses in a given amount of time. The charge is just going to be, if it goes around once, one electron has passed that loop. And the time it takes to go around once is just distance over time. Distance divided by velocity. The distance is the circumference of that orbit, 2 pi over r, and whatever velocity it's going at, right? If we want to look at the magnetic moment of a current carrying loop, that you should remember from intro physics, is just the current times the area of that loop, right? The area would be pi r squared, and we just calculated the current. So this ends up being equal to QV over 2 pi r, the current, times the area of that loop, pi r squared. We get a bunch of, a bunch of cancellations, and we get the magnetic moment magnitude is just going to be QRV over 2. Now, another thing we can do is we can cast this in terms of the angular momentum of that electron. So if we think of our angular momentum, we know that that is r cross our regular momentum, or r crossed with mass times velocity. And if we're looking at just keeping this in the plane and we want the magnitude perpendicular to that plane, this is just going to be mv times r. So we can take this angular momentum and make a substitution into our magnetic moment, and our magnetic moment then becomes q over 2m times the angular momentum L. And this is what we would classically expect the magnetic moment of an electron orbiting the nucleus of an atom like that. So we have some magnetic moment proportional to the orbital angular momentum. Turns out that there's a type of angular momentum called orbital angular momentum. Another thing that we can actually look at, though, is if we consider that electron, classically, if we were to consider it just a sphere that is spinning with some omega around a given axis, that as well, if we take that ball of charge and take a chunk of it, that's going to look like it's going in a circle. We can do the same sort of analysis here and try to figure out, well, if this is spinning, a ball of charge spinning, what would the magnetic moment be associated with that spinning ball of charge? The math isn't as straightforward as this. You'd have to do an integral over the charge distribution and all this, but you end up with the same sort of result, where you end up with a magnetic moment is equal to G times Q over 2M times what I'm going to call S, which is the angular momentum associated with the spinning of that object. G here is what we call the gyromagnetic ratio or gyroscopic ratio. Again, you have to do the details of all the integrals in that to get what we would expect that to be. But the point is, for a given spinning ball of charge, we would expect the spinning part to have an angular or magnetic moment associated with that spin angular momentum. Again, both of these, though, in classical mechanics, classical analysis doesn't have any quantization. Nothing in here indicates there should be two values, depending on the alignment of how this is spinning or how this orbit is, they could be pointing in any given direction. So again, classical mechanics is failing to account for the results of the Stern Gerlach measurement. It fails to say why the Z component, that essentially we measured the Z component of the magnetic moment, why that would be quantized into two results. So what have we got so far? Well, we've taken our Stern Gerlach experiment, which took an oven, shot some neutral silver particles through a magnetic field gradient, and we saw it split into two possible values of the magnetic moment in the Z direction. Turns out that maps directly to two possible values of the angular momentum in the Z direction. Specifically, what this was looking at is the spin angular momentum of that silver atom. If we were to try to analyze this as we've sort of done today using classical physics, it totally fails to account for this. We would expect just sort of a broadened smudge sort of band where particles hit everywhere along here. But that's not what we see. We see this distinct quantization of the spin angular momentum. It turns out those two possible values, if you take the spin and the z component of the spin on those particles, we get two possible values, and they are equal to plus or minus h bar over 2, where h bar is just the reduced Planck's constant, which is Planck's constant divided by 2 pi. This is sort of the big result of the Stern Gerlach experiment. It shows the quantization of angular momentum, specifically the spin angular momentum. Next class, we're going to look at just sort of some conceptual experiments that are built off this idea where we can send a beam through a field gradient and split it into its quantized components, and that'll sort of lay the foundation and outline a lot of the weirdness and things, unusual things that come with quantum mechanics. And it'll slowly build us into, well, how do we treat this properly using quantum mechanics? Before this ends, though, I want to just point out one thing. We've sort of built our vocabulary using this classical physics. We've started to define there's some spin angular momentum that appears to be quantized. And the name spin comes from this sort of thought of it being a spinning ball of charge. There should be angular momentum associated with that. That is not how we should think about spin, though. Electrons are not balls of charge spinning. There's a lot of things wrong with that idea. The way I think it's best to approach spin, it is the intrinsic angular momentum with a particle. So you should think about it the same way as we think about charge. There's a positive E fundamental charge for protons, a negative E fundamental charge for electrons. That doesn't come from some other thing. Just like this spin angular momentum, it is an intrinsic fundamental property of an electron. It is not because it's some charge spinning or anything like that. But anyway, next video, we'll go through some experiments built off this Stern Gerlach setup and start to get into how quantum mechanics will deal with all this.